Okay, so for number 1, y varies directly with x. Now remember, direct variation is a constant ratio. Y over x equals a constant. So what that means is we can take a starting condition, y is 18 and x is 4, and make it into a ratio, and the other condition has to have the same ratio. We're looking for y, that goes on top because the 18 was a y. X is 4, and x goes to 10, so we put 10 on bottom, and we cross multiply and divide. 18 times 10 is 180, divided by 4 is 45. So y is 45. Y varies inversely with x. When I say inversely with x, remember that is a constant product. X times y equals a constant. So over here we have y is 8 when x is 6. So that's 8 times 6. It has to stay the same. Find y, so y times when x is 4. Y times 4. So we're going to multiply and divide here. It's just not cross multiply and divide. 8 times 6 is 48 equals 4y. Then we divide by 4. So 12 equals y. Now you'll notice the difference here. When it varies directly, x got bigger, it went from 4 to 10. Y got bigger, went from 18 to 45. Varies inversely, x got smaller, went from 6 to 4. Y got larger, went from 8 to 12. Inversely means just that. They do the inverse or the inverted, the opposite. One gets bigger, the other gets smaller. Any questions on those? Okay, so today what we want to talk about is we want to talk about angles. To talk about angles, we're going to go back a little bit. We've mentioned before that everything in geometry starts from this little thing right here, a point. That point is nothing more than a location. And we can take that point and we can drag it in a single direction to make a line segment. And we talked about the length of that line segment equaling the distance that we move the point. Well, if we take that point and we move it in a single direction and we just keep on going forever and ever, we create what's called a ray. An array can be described by two things: the location of its starting point and the direction that it goes. This one's going off to the right, or if you're thinking like a map, you might say the east direction. The location of the starting point is easy to describe. It's the direction that took some working. And it started out based on navigation. In navigation, 0 direction, the east direction is 0 degrees, and it goes around counterclockwise. Now 90 degrees, 180 degrees, 270, and then 360 was back at 0 again. So I might have a ray. The starting point is always at the center of that compass rose, or whatever you want to call it, center of the graph. And the ray is moving that point in one direction or another. So this ray, let's say that angle there is 29 degrees. So this ray has a direction of 29 degrees. To form an angle, we have to create a second ray from the same starting point. So we're starting at this point, we're going off in a slightly different direction. Let's say the direction of that one is, let's go 68 degrees. The size of the angle It's just the difference in direction. So here, this angle right here, we have a 68 degree and a 29 degree. We subtract those, that's 39 degrees of difference in direction. That's a 39-degree angle. Now, through time, navigation became a skill that was not so popular, not so common. Most people didn't know much about it. So they shifted the definition of an angle a little bit. If I'm going in a certain direction and I stop and I turn all the way around, so I'm going back still in that same direction, how many degrees did I turn? 360, one complete turn. If I'm walking in a direction and I stop and I turn and I'm going back the exact opposite direction, how many degrees did I turn? 180. How do we figure that out? Yeah, half of 360, divide by 2. If we're going in one direction, we stop and we turn exactly off in a square corner direction, perpendicular direction. How many degrees have I turned? 90 degrees. Good. Again, that's just 1/4 of a complete turn. So it got to where we started to define angles as a fraction of a complete turn. 20 degrees means that it is 20 3/60ths of a full turn. So anyway, let's look at some relationships with our angles. So let's say we have an angle here. Let's call this one 31 degrees. And we create another ray, a third ray from the same vertex. Let's say this one here is 65 degrees. Two angles that share a vertex and a side are called adjacent. And the nice thing about adjacent angles is they are additive. In other words, we can add or subtract them. If I want to get this whole angle here, I'm just going to take 31 degrees plus 65 degrees to get 96 degrees total. Is that whole angle? Obviously not quite drawn to scale. Or on a similar note, if I told you that this angle here was 72 degrees, and that this angle here was 21 degrees, and I asked, what's this one here? Well, I can subtract. 72 is the whole thing, minus the 21 degree piece gives me 51 degrees. What do you think? There are special combinations of those adjacent angles. We might have this situation. Let's say we are told that this angle here is disappearing. 108 degrees. What's this angle have to be? How do we find that angle? Perfect. 180 minus 108 gives us 72 degrees. This has to be a 72-degree angle. Two angles that add up to a straight line, or two angles that add up to 180 degrees, are called supplementary. Now, along with that, this little square there in the corner means it's a square corner or a right angle. If I tell you that this angle here is 31 degrees, what's this one have to be? How would you find it? 90 minus 31 gives us 59 degrees. Good. Two angles like that add up to a right angle, or two angles that add up to 90 degrees, are called complementary. Now, if you're anything like I was when I first learned these, I could remember the words, but I had a hard time remembering which one was which. Well, 90 degrees makes a right angle, and you get complements when you're right. Should probably talk a little bit about this. This is 90 degrees, and that is called a right angle. What's it called if we have an angle that's smaller than a right angle? Acute. You can think of it usually things that are acute or small. So an acute angle is smaller than a right angle. An angle that's larger than a right angle is called obtuse. Comes from the same root as obese. Obtuse means large. Those words get used outside of math. Somebody who's an acute thinker is able to look very narrowly and see the details in a very narrow band. Someone who's an obtuse thinker is able to step back and see the whole big wide picture. So if I tell you that this angle here, let's say that it is 2x minus 1, and that this angle over here we might have as let's do 3x plus 31. How would I find what those angles are? What do I know about the relationship between those two angles? They add up to 180. So 2x minus 1 plus 3x plus 31 has to add up to 180. I can combine the 2x and the 3x to make that everybody at once. 5x. Negative 1 and positive 31 to make 30. And now I can solve my equation. What am I going to do first? Positive 30, by the way. I'm going to subtract the 30. 5x equals 150. And then divide by 5. Gives us x equals 30. Now I wasn't asked to find what x is. I have to find the angle. So I need to go back up here. X is 30, so this is 2 times 30 minus 1. 2 times 30 is 60, minus 1 is 59. I'll do the same over here, and I'm going to have to double check to see if they make sure they add up to 180. So 3 times 30 plus 31. 3 times 30 is 90. Plus 31 is 121 degrees. 121 and 59 do add up to 180. So that tells us that, well, we're pretty confident that that's the right answer. Other relationships we can run into based off of that. Let's say I tell you that this angle here is 38 degrees. What's that angle? How would I find that angle there in the green? Well, this across here is a straight line, so those two angles add up to a straight line. So it's 180 minus 38 equals 142 degrees. How would I find this angle over here in the blue? Yeah, that's also a straight line there in the darker brown. So yeah, that's 180 minus the 142 gets us back to 38 degrees. So if I wanted to compare the angle in red here to the angle in blue, they're the same. And that's what we call vertical angles. Anytime two lines intersect, it forms two pairs of vertical angles. The vertical angles must be equal. And the reason they're equal, the 38 and the 38 here, because they're both supplementary. They both form straight lines with the 142. So there's only one angle that's supplementary to 142. That's 38 in both directions. Of course, this angle down here would be 142. That's vertical to that one, the 142. So they have to be the same. And of course, it is also supplementary to both the 38. So it has to be 142.
I can learn to understand you much better if I can get familiar with the...
Okay, so with all this now involved, let's take it to the next level. I want to find each of those angles. What do I know about the relationship between them? They must be equal. Very good. So 5x minus 27 equals 2x plus 3. Now, before we can solve that, what must we do? Yes, we have to get it down to just one appearance of the x. Well, there's one on each side, so we're going to get rid of the smaller one, the 2x. 5x minus 2x is 3x. Minus 27 equals 3. And then we add 27. 3x is 30. And then divide by 3. X equals 10. Now we have to still go back and find the angles. So this is 5x becomes 5 times 10 minus 27. 5 times 10 is 50 minus 27 is 23. This is 23 degrees. Now we could just assume it is the same. Let's double check. 2x becomes 2 times 10 plus 3. 2 times 10 is 20 plus 3 is 23 degrees. So yes, that does appear to work out. These two lines are called parallel. We're used to defining parallel lines as lines that never intersect. And as long as they're on a flat piece of paper, on what we call a plane, never intersecting does make them parallel. But in 3 dimensions, that doesn't work. If you imagine I have this line and this line, do those intersect? No. Are they parallel? No. So the technical definition of parallel, so that it works in 3 dimensions, is always the same distance apart. Technically, the wording is everywhere equidistant, always the same distance apart. Now, when we have any two lines that is cut by a third line going across both of them, that line that cuts across them is called a transversal. The transversal, of course, is most useful when it cuts across parallel lines like this. If I tell you that this angle here is 61 degrees, if I look at this other line here, if I slide that up to be on top of the other one, I'll notice that 61 degree angle has to match up with this angle down here as well, doesn't it? That's also 61 degrees. Well, if those angles are 61 degrees, What can I say about these two? Those are also 61 degrees because they're vertical to those, right? These original two angles are what are called corresponding angles. You don't need to write that word down. There's a lot of vocabulary involved with the angles when you talk about parallel lines cut by a transversal. There's interior, exterior, alternate, corresponding, all sorts of vocabulary. And they define some as being equal and whatever. All we're concerned about is finding what the angles are. What would this angle have to be? How would I find it? (180 minus 61, right? It's 119 degrees. Those two form a straight line. They have to be supplements. What would this angle be? 119. This angle, 119, and this angle, 119. When parallel lines are cut by a transversal, there's only two angles formed. So when you look at those parallel lines cut by a transversal, the angles formed, if you know one angle, all the other angles are either equal to it or supplementary to it. Pretend those are parallel. If I give you that this angle here is 123 degrees, what's this one have to be? Perfect, 57 degrees. 180 minus 123. Obviously not equal to it, so it must be supplementary to it. This one, of course, is the 123 itself. Well, the last angle relationship we want to look at is a relationship in a triangle. The three angles in a triangle have to add up to what? 180 degrees. It's called the angle sum. The angle sum of a triangle is 180 degrees. So if I know these two angles, I can find this one. By adding those together, 81 plus 58 is 139 degrees, and then subtracting it from 180. 139. So this has to be 41 degrees here. Makes sense? Pretend that's an arrow. If that angle there is 48 degrees, this angle here is 39 degrees, what does this angle here have to be? Throwing in 48, very good. If we look at the lines that are really of use there, we have the parallel lines and the transversal. The 48s are cut by the transversal. They have to be the same. So what if I ask about this angle here? It's vertical with that one, isn't it? So that means that these three add up to 180, right? So 48 plus 39 is 87 degrees. So this is 180 minus 87, that's 93 degrees for that angle. That means this one is 93 degrees. Make sense? There's a lot of different combinations you can find in these angles, a lot of kind of puzzle pieces you put together. I'll let you guys get your homework. Your homework's going to be on page 403. Exercise 12-1. 1 through 35, the odds.